I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. I want to make a video today to introduce using Google Sheets or any spreadsheet program, computational software program, to help solve and visualize some problems in biological thermodynamics in general. Today specifically, I want to look at something we commonly do in which is changing phase of material. And almost always we'll start by looking at water because of its importance as a substance, etc., and our familiarity with it. We have familiarity with it in its solid form as ice, its liquid form as water, and as steam, or it's in its vapor or gaseous form. And so we have an intuition of this already, and we often are asked to work problems to see how the energy changes. How much energy do you need to take something like an ice cube and melt it, to take that liquid water and boil it, etc. And so we want to look at some of these processes, either in that direction or to take steam and condense it, to freeze water, etc. How much energy do you have to take out of the system to be able to do these type of things? So we work a lot of problems like that, but one of the things I find is that a lot of times you get a procedure for how to work these problems, how to change use the heat capacities over temperature ranges and the delta S or H of fusion and vaporization, etc. But we get lost in the calculation and often don't step back and just look at a few things. And so that's what I wanted to talk about today and tell you what I often do, which is I usually put it into some type of computational package like Mathematica or something I can visualize it in, make plots. And there's a whole range of different things, from scientific plotting packages like Sigma Plot, Origin, Kaleidograph, etc., to ones that handle symbolic math and plotting and will let you do analytical or numerical calculations like MATLAB or Mathematica or Maple. But one of the simplest that we all have access to is just spreadsheets, and they'll do plotting as well. And while they're not maybe designed for scientific stuff, oftentimes you can get them to work very easily, and it's something we ubiquitously have available to us. So I'm using today Google Sheets because you can go to it at any web browser. It's free, easy to use, and it more or less works like Excel or any other spreadsheet, etc. And I've done something where you would say is very common, which is just looking at the phase transition, from solid ice, through liquid to gaseous. So the exact problem that this one was meant to solve was if you start with ice at minus 20 degrees, so in your freezer, which is a pretty common temperature for a freezer, minus 20, you take that ice out and you heat it through its liquid all the way to gaseous state, to a final temperature of 120 degrees Celsius. So your initial state was ice at minus 20. Your final state was steam or vapor, water vapor at plus 120 degrees. You do this under constant pressure conditions. How much energy does it take, to do that? How much energy do you have to put into the system? What's the change in energy? So the energy we're going to look at under constant pressure conditions, most naturally, is the enthalpy. So we can look at the enthalpy because that's equal to in a sense, the amount of heat directly. And then the other thing is to look at the entropy of the system. And this is pretty common under constant pressure conditions to think of, to look at the energy in a system through its enthalpy and through, entropy to see, how things are happening and how the overall free energy of something is changing, right? So, what I typically do is get all of the thermodynamic constants, which you can look up at numerous websites, in lots of textbooks, at NIST, on Wikipedia. If you just type in, water in its various forms, you'll easily find values for the heat capacity, which I've listed here, the formation, enthalpy, the entropy, the standard state entropy, and you can usually even find, in a sense, the combination of these two, its Gibbs free energy. Also, we're going to be going through phase transitions. So we can also look up, the enthalpy and entropy of fusion, and the entropy and enthalpy of vaporization, which we'll need as well, right? And so we can start with something at, say, -20, and we can use its CP, its heat capacity over a temperature range to get us, from -20 to 0, right? Now at this point, it becomes discontinuous, and we have to use, the delta S of fusion, which we have right here, to be able to get us at 0 degrees from the solid state into the liquid state. That's the fusion of a, solid into, the liquid state, or in other words, the delta S of melting. Then once we do that, we can again take the heat capacity now of the liquid state, which is higher, and we can do that over a delta T till we get to 100 degrees Celsius. Now again, it will go discontinuous because of vaporization, and we can look at the delta S vaporization at 273, which is where it's boiling. It'll discontinuously change there. We'll take that into account, and then we can now take the heat capacity of the vapor from 100 to 120 degrees. And so you can see that's what I've done here. These continuous, and then it has a discontinuous jump at 0, which is the delta S of fusion. And then you go along continuously, and it has a discontinuous jump here at 100. And then we go to 120. And I've gone a little further on each bound. Now, these are, being calculated. So, these are formulas where I'm going over a CP, ln of T, a final temperature over initial temperature for each of these and adding it to each one of these components. So these are calculating it based on these values. And if I change these values, it will change, what these numbers come out at, so that you can then make adjustments. And that's one of the nice things. Instead of having to by hand recalculate everything, I can just change a number here, like, oh, I missed the heat capacity, and change it, and it'll show up there. The thing I find best about this, though, almost every time I'm using a spreadsheet, it's also to do something to make it visual. And so, when I plot this, the temperature versus the entropy, from, -20 to 120 here, now you can visually see what we're talking about. You go, the entropy increases just a little till you get to 0 degrees Celsius, and then you get the discontinuous change from fusion, and then it goes up with a little bit greater of a slope because the heat capacity of water is greater. Then you get your delta S of vaporization, and the vaporization is much larger. It's 109 compared to fusion, which is only 20. And then you can see this, the slope is even shallower for steam because its heat capacity is even shallower. And you can even tell that basically, you don't add a lot to the entropy, between -20 and 0, and between 100 Celsius and anything higher, because these are such shallow slopes. It's really most of the entropy is coming when you fuse, when you melt, and when you boil the water. And so if you just add up, the fusion and the vaporization, so about 110 and another 20, right? So we'll get basically around 130. That gives us about what we get, when you add, and you just get a little more than that because of these positive slopes that give you a little more. And like I said, you could come in here and say, oh, maybe I missed the heat capacity. Maybe we had something that's much larger. And so the heat capacity is, much larger, and you can see this slope change now. So we could, exacerbate it and, make this slope much larger, by changing its heat capacity, or take it back down to, the value it was, right? And you can see how changing these parameters will change this as well. So, this is how I feel you can get a much better intuition for some of these, which in this case is realizing that because of these fairly shallow slopes over temperature ranges, that most of this can be estimated just by taking into account the fusion and vaporization. And you can tell that of the two, it's the water, because of its higher heat capacity, that adds more to the entropy when you change it. So I hope this gives you a concrete example and ways that you might be able to use spreadsheets in helping you not only look at phase transitions. There's really most aspects in both chemical and biological thermodynamics. You can apply these type of principles to making spreadsheets that make things in fairly graphical ways. Thank you.